All right, guys, today we're just going to do about half of these notes, starting with the definition for a rational function. This is our AP Pre-Calc definition. A rational function is analytically represented as a quotient of two polynomial functions and gives a measure of the relative size of the polynomial function in the numerator compared to that of the denominator for each value in the rational functions domain. That is a very fancy way of just saying, like, for example, actually I want to throw one extra piece into this. The two polynomial functions, the numerator and the denominator, need to have a degree 1 or higher. So an example of a rational function could be like f of x equals, give yourself some sort of polynomial in a numerator, it doesn't matter what it is, some sort of polynomial, any degree, whatever, in the denominator. But I couldn't just do, so this is rational, but not rational would be this. X squared plus x plus 4. If I just had it divided by -4, because that's not a rational function, that's just a quadratic function, right? It's a quadratic function with a -1/4 being multiplied out in front. So even though it doesn't specifically say degree 1 or higher, we are assuming that you should assume that you have an input variable show up at least once in the numerator and denominator. All right, now I know that you graphed rational functions in Algebra 2. There are a lot of little rules to think about, and we're going to throw in some limit notation for AP Pre-Calc and to prep us for calculus. So that's where things will be a little bit different. Hopefully some of these rules sound familiar though. So a vertical asymptote is a value x equals a, where f of a is undefined. But it has to be a little bit more than just that, because we'll talk about in a minute. We could have a discontinuity called a hole in the function, where f of a doesn't exist. So we're also going to say where f of a doesn't exist and f of x is unbounded as x approaches a. What does unbounded mean? So if we're near a vertical asymptote, so let's say there's a vertical asymptote at the vertical line x equals a, the values of the polynomial in the denominator will be so close to 0 that the overall function is either going to be an incredibly large number or an incredibly negative number, and so it's going to increase or decrease without bound. So let's look at just the parent function for rationals, 1 over x. We know that if we plug in 0 when x is 0, f of x is undefined, right? If we look at values that are very, very close to 0, let's start a little bit farther away, like -0.01. I don't have my calculator open, and I don't really need to fire it up at this point. It's kind of nice to look at this as a fraction anyway. That's -1/100th, right? So what is f of x when I plug in 1 over -1/100th? Well, we know that that's the same as 1 times -100. So if we're close to 0, a little bit to the left, we're at -100. If we get even closer to 0, so an even smaller negative decimal, so it's even closer to 0, this is, oh gosh, what is this? Let's see, 100,000, 10,000, 100,000. So this is -1 over 100,000. Hopefully I did my math right on that. Yeah. Then when you plug in 1 over x, you're going to get -100,000. And you can see if I were to keep going, I could get -1,000,000, -1,000,000,000, -1 trillion. I can keep adding decimal places to this, and my function is decreasing without bound. Okay, and so I'm going to say as x approaches 0 from the left, these were like negative values, that was to the left, f of x approaches -infinity. And the same thing would be true on the positive side, right? If I plug in 1/100,000th, I'm going to get 100,000. If I go a bit further out, I get a smaller number, but the closer I get to 0 from the right side, as x approaches 0 from the right, f of x approaches positive infinity. And we know about this graph, right? Our parent function, oops, I should probably sketch it correctly. We know about this graph. Our parent function puts a positive branch here for 1 over x and a negative one here. Right, we've seen this graph before and we've transformed it. And yeah, as we get close to 0 on the left side, the graph is headed down. As we get close to 0 on the left side, the graph is headed up. So instead of writing this out in words, we have this really handy limit notation, which we've seen before with our polynomial behavior. So we're going to use something called one-sided limits. So vertical asymptotes could be written like this. The limit as x approaches a, which is the vertical asymptote, that little negative sign means from the left, could either equal positive or negative infinity. And the limit as x approaches a, that little plus sign means from the right of f of x, that could equal positive or negative infinity. So for this example, instead of writing this out in words, I could say the limit as x approaches, what was our vertical asymptote? It was at x equals 0 from the left of f of x. What was that limit? I said it was the graph was approaching negative infinity, so that limit is equal to negative infinity. The limit doesn't exist. We're just telling you which direction the graph is headed. And the limit as x approaches 0 on the right of f of x is equal to positive infinity. So this is limit notation, says the same thing as what I wrote out in words. You're going to be expected to be able to use and read limit notation for our AP exam, and you'll use it a lot in calculus next year as well. So all we're going to do is determine the equation, or there could be more than one, equations of vertical asymptotes for each rational function. And then we're also going to, once we write down those equations, like x equals whatever, we're also going to use limit notation to figure out what the function behavior is. And I want to do this numerically, and then I also want to confirm on a graphing calculator. Again, we're not going to do this every time, but this is good practice as we're getting into some of this limit notation and just kind of getting comfortable with it. How do we find a vertical asymptote? A vertical asymptote is setting the denominator equal to 0. Because remember, we said it's the value x equals a where f of a is undefined, and the only way for a rational function to be undefined is if its denominator is equal to 0. So if the vertical asymptote should be when x minus 4 is equal to 0. The negative 3 does not factor in here. So there's a vertical asymptote at x equals 4. So this is the equation for the vertical asymptote, right? And then let's think about this. What is the limit as x approaches 4 from the left of negative 3 over x minus 4? Or I could write f of x. What number is that going to, or what way is that going to be? Is it going to be positive or negative infinity? And what about the limit as x approaches 4 from the right of negative 3 over x minus 4? Before we dive over to our graphing calculator, think about this numerically, kind of like what I did with the table. We want to pick a number where, think about 4 being in the middle here. If this is 4, what's a number right to the left of 4? Like 3.9, right? 3.99, 3.999. And to the right would be like 4.0001. Okay, so to the left would be like, think about plugging in let's just use 3.9. We don't really have to get extreme. We're just saying, are we going to get a positive or a negative? If we plug in 3.9, we get negative 3 divided by 3.9 minus 4. That's negative 3 divided by negative 0.1. That's positive 30, right? 3 divided by 1/10. And if I would have picked 3.99999, it'd be negative 3 divided by negative whatever. Take this out to more zeros. So the point is, if you plug in anything to the left of 4, you're going to get negative 3 divided by something else that comes out negative, right? Because you're plugging in a number smaller than 4. A negative divided by a negative will always be positive. So this is headed toward positive infinity. So I'm going to make a note here for my notes. The fact is that that's positive. Not so much that it's 30, just that it's positive. And we can examine a number very close to 4, but to the right of 4. So maybe 4.1. We can say, well, we would always have negative 3 in the top, and then like 4.1 minus 4. So that would be like negative 3 over 0.1. So that would be an always negative divided by a tiny, tiny positive. In this case, I just get negative 30. But again, if I take this out to more places, like if I did 4.000001, I would have a lot more zeros on here as well. So that's just to say that we're headed toward negative infinity there. What does that mean graphically? Let's check this. So this is negative 3 divided by parentheses x minus 4. I'm just going to zoom, oops, I'm just going to zoom 6. So as we approach 4, what did we say? On the left, to the left of 4, the graph should be heading toward infinity, which it is. To the right of 4, as you approach 4, but you're coming at it from the right side, your graph is headed toward negative infinity. So yeah, that checks out. Let's do it for number 2, the vertical asymptote. This is already factored for us. We're saying when is x plus 2 squared equal to 0? That's just when x equals negative 2, right? The squared doesn't matter. So the vertical asymptote equation, x equals negative 2. If I had to describe the behavior, maybe this is a non-graphing calculator section of my AP exam, I could say, well, the limit as x approaches, we're talking about negative 2, from the left of, you can either write g of x, or I like to write the expression in so I can see what I'm supposed to plug into. What is the left-handed limit? So first of all, be careful with your negatives. Here's negative 2. What's a number to the left of negative 2? Negative 3. But what's something that's really close but not quite negative 3? Like maybe like negative 2.1. And then what's something on the right of negative 2? Well, negative 1, but you don't want to jump that far, so get closer. Negative 1.9 would be awfully close, but still to the right of negative 2. So sometimes a little number line is helpful. I could have done that up here too. Here's 4. 3 is to the left, 5 is to the right, but we're thinking like small, 4.1, 3.9. All right, so let's see what this comes out to. So if we plug in negative 2.1, well, we've got this positive 4, and yeah, when you plug in negative 2.1 plus 2, you're going to get a negative, but then you're going to square it. So the point is not what number are you getting, it's that you're getting a positive divided by a tiny positive number. Anytime you divide by a really tiny decimal, remember it's like multiplying by the reciprocal. So if you're dividing by 1/1,000,000th, you're actually multiplying by 1,000,000. So this graph is headed toward infinity if we're looking to the left of negative 2. And then the same thing should be true on the right, correct? Like the limit as x approaches negative 2 on the right, if I plug in negative 1.9 into 4 over x plus 2 squared, it doesn't matter if I plug in negative 1.9, it's still going to be 4 over something squared. And yeah, it'll be positive 0.1, but the fact is that it's still a positive divided by a teeny little positive. So you're also going to get positive infinity for that. So this graph, as we approach negative 2, should shoot up in both directions. So let's verify that. It was 4 divided by the quantity x plus 2 squared. Yeah, so it's the graph is whether you're on the left of negative 2 or whether you're on the right negative 2 approaching negative 2, you're headed toward infinity. We are going to focus mostly on just finding the vertical asymptote, but when I assign some AP Classroom problems, I'm going to try to look for limit notation as well. Okay, what about holes in the graph? I briefly mentioned that. Holes in the graph also occur when there's an a value where f of a is undefined, but there's sort of this extra caveat. You need to find a hole in the graph, you simplify the rational function if possible. That means factor, cancel what you can, which is why we did that rational expression unit a few days ago. Any factors in the denominator that divide away or cancel out or whatever, they're no longer present in the simplified function. Those are holes in the graph, and they're not vertical asymptotes. So you can't be both. You're either a vertical line or you're a hole in the graph. You don't get to be both. To plot the hole in the graph, you have the x value already. It's whatever canceled out. It's the 0 for that x value. I'll show you that in a minute. But you have to plug into the simplified function, because if you don't, you'll keep getting that you're dividing by 0. So we do plot holes in the graph. We plot them with an open circle because this is a discontinuity. We need to show that there's a hole in the graph, something like this. Okay, find all vertical asymptotes and holes in the rational function. So we're not going to use limit notation. We're just going to find our information here. So the first thing to do, remember, simplify as much as possible. So factor what we can. I've got x plus 4, x minus 2, x plus 2, x minus 2. So these x minus 2's cancel. So my simplified function is x plus 4 over x plus 2. But if you were to go to graph this thing, the original function was not the simplified version. So the graph is going to look like x plus 4 over x plus 2, except it's going to have a hole at x equals 2. And there is a vertical asymptote at x equals negative 2. Okay, find all vertical asymptotes. Done. There's one at x equals negative 2. At x equals 2, there's a hole. I want to find the ordered pair for the hole. So it's not enough to say it's at x equals 2. I need to be able to plot that point. A hole is a point. It's an ordered pair. So remember, you're plugging into the simplified f of x. F of 2, if I plug it into the original, I would get 0 over 0. That's no good. But if I plug it into this, I get 2 plus 4 over 2 plus 2. 6 over 4 is 3 over 2. So that's the hole in the graph. I would plot this with an open circle. All right, next one. This is g of x. So the numerator factors into x plus 4 squared. And the denominator, you can factor 2 out. So here's one where the x plus 4 in the denominator can cancel with one of the x plus 4's in the numerator. So our simplified function is just x plus 4 over 2. And so again, the original graph looks like this. X plus 4 over 2, that's not rational anymore. That's like 1/2 x plus 2. So it looks linear. It's not linear. It's not a linear function. It looks linear with a hole. Where's the hole? The hole is at x plus 4. So x equals negative 4 is a hole. And g of negative 4 is 1/2 times negative 4 plus 2. Negative 2 plus 2, 0. So, sorry, back on my other one, the ordered pair 2, 3 over 2 is the hole. Here, the ordered pair negative 4, 0 is the hole. And there is no vertical asymptote because the only denominator that had an x divided out. So instead of a vertical asymptote, it's actually a hole in the graph. They're called removable discontinuities. Like you remove that factor, you can kind of create a piecewise function to say, well, here's the function, except it's this when x equals negative 2 or whatever. And then a vertical asymptote is a non-removable discontinuity. All right, for this one, let's see, I'm just going to factor up here a bit. X plus 6, x minus 3. Okay. Now, what about this? We have an x minus 3 that canceled, right? So is there a hole at 3 or is there a vertical asymptote at 3? So that's kind of tricky, right? Because we just said, well, if a factor cancels out, then it's a hole. But the trick to that is actually h of x equals x plus 6 over x minus 3 if I simplify. So there's not a hole at 3, there's still a vertical asymptote at x equals 3. Basically, if an expression survives the simplification process, so if it's still there, it's no longer a hole, it's still a vertical asymptote. If we were to graph this h of x, the graph would increase without bound at 3. It's not going to continue on its way. Okay, what about horizontal asymptotes? These are kind of rules to memorize. Again, I tried to use some of the AP Pre-Calc language, although we're going to simplify it a little bit just for our own memory. So we talked about end behavior with polynomial functions. With rational functions, the end behavior doesn't have to increase without bound. It doesn't have to go to infinity or negative infinity like polynomial functions do. So instead, end behavior is affected the most by the polynomial, whether it's in the numerator or denominator, with the largest degree. That is what's guiding the overall behavior as you start plugging in really large positive values or really small negative values. Horizontal asymptotes don't have to exist. So if they exist, then your rational function levels out to some value. If not, it can increase without bound or decrease without bound. So scenario 1 is if the polynomial in the numerator has a larger degree than that of the denominator. So in our brains, we're thinking top heavy. Higher degree on top than on bottom, like x cubed on top, x squared on the bottom. If it's top heavy, then the polynomial has no horizontal asymptote. Because if you were to do long division, you would get some sort of function that increases without bound or decreases without bound. If the polynomial in the numerator has a smaller degree than that of the denominator, which we consider to be, I just think, bottom heavy, like the x cubed is on the bottom, the x squared is on top, then in the long run, those values are going to divide out to get smaller and smaller and smaller and practically be zero, even if they're only different by 1 degree. So there's a horizontal asymptote of y equals 0. No matter what numbers are in front, if it's y equals 3x squared over 4x to the third, the horizontal asymptote is y equals 0. Right? Plus some other stuff I should have said. Okay, if the polynomial in the numerator has the same degree as that of the denominator, so they're both cubed or they're both squared, which I call that a tie, then the polynomial has a horizontal asymptote of y equals a divided by b. So a and b are the leading coefficients in the numerator. So for example, if we have, let me use my same example, 3x squared plus some other stuff over 4x squared plus some other stuff, then y equals 3/4 is the HA, horizontal asymptote. Okay, so let's just practice those rules. Write the equations of the horizontal asymptotes if they exist. And then I also want to use limit notation again because, again, we might be asked to do that. So first, let's just apply the rule. The degree in the numerator here is 2. The degree in the denominator is 2. So this is a tie. So the rule is that the horizontal asymptote is y equals 3 over negative 6. Divide the leading coefficients. Simplify that, of course, to y equals negative 1/2. How do I write that in limit notation? So with rational functions, what a horizontal asymptote is saying is the limit as x approaches, let's just say infinity. Well, actually, it's plus or minus infinity. Whether you go way far out to the right or way far out to the left, the limit as x approaches those values of a of x is equal to negative 1/2. This is just saying if you were to graph this thing, the y values level out in the long run to -1/2. All right, what about the next one? We have x cubed minus 27 over x minus 3. And even though I could do a bit of factoring and simplify this, I don't need to. This is top heavy. And if it's top heavy, there is no horizontal asymptote. It doesn't mean you can't graph the thing. It just means it doesn't level out. And actually, you can look at some division to figure out, like, well, what if I do divide x minus 3 into x cubed minus 27? So let me just apply my factoring the difference of cubes real quick. So b of x should look quadratic. If I were to graph it, it should look like the quadratic x squared plus 3x plus 9, but it's got a hole at x equals 3. Right? So that's what happens. If you have something that doesn't have a horizontal asymptote, it just means it looks like a polynomial function of some other sort. If you do the long division or if you do simplification, you'll see what shape it should have. Okay, and then this one, sometimes you're not given one of the polynomials or both of them in general form, they're in their factored form. So you do need to think, what would this be if it were FOILed out? You should, if you're going to FOIL it out, do it correctly. You don't really need to, but so this would be x squared, right, over x to the third. That's bottom heavy. So y equals 0 is the horizontal asymptote. Okay, so limit notation for that would be the limit as x approaches either positive or negative infinity of c of x is equal to 0. All right, last thing for today, slant asymptotes. So I just got done saying if you have a top-heavy rational function, there's no horizontal asymptote. It doesn't mean there's no asymptote at all. So there's a special case. If top-heavy by 1 degree, and I know I just wrote out what this says, but I just want to have a shorter version of it. So if the polynomial in the numerator is larger than that of the denominator, so top heavy, by 1 degree, then there exists a slant asymptote. How do you find it? It's going to be a linear equation. You can find it by performing long division, or synthetic if it applies, but long always works. And then you can examine the result that you get. You're basically ignoring the remainder, but we'll talk about that, examining the limit as x increases without bound. First, let's just do the division. So top heavy by 1 degree, yes, x cubed over x squared. Long division, remember you've got to put in some placeholders here. This is not out of our lives yet. The good news is when you're doing long division with these, it's not going to be a lot of steps. You multiply x squared by x to get x cubed. So go through these steps. We subtract all of that. X cubes are gone. 0 minus 0 is 0. 2 plus 1 is 3x plus 1. And remember, you're finished with long division as soon as you get something that's a degree lower than what you have. So what we have for the slant asymptote is so far it's y equals x. And then remember, this is a remainder. We write it as like 3x plus 1 over x squared minus 1. Now, what is this about the limit equation? Because that's not the final slant asymptote equation. The slant asymptote is just going to be y equals x. You can remember this by just saying, just ignore the remainder. But why can we ignore the remainder? Because remember, asymptotes are saying, what's the limit of this thing as x approaches positive or negative infinity without bound? Well, we would get infinity or negative infinity here, but I'm talking about this little piece here. What will we get here? This is bottom heavy. It would become 0, right? So the limit as you approach infinity or negative infinity would be this x value, whatever number you're plugging in, plus essentially some really small fraction, close to 0. So for that reason, we say basically ignore the remainder. And when you do long division, just write down the quotient that's at the top, but not the remainder. So this would have the line y equals x as its slant asymptote, which means whatever the graph does in the middle, eventually, maybe there's some fluctuation here, eventually it follows the behavior of that slant. Okay, let's do this again. Top heavy by 1 degree. So let's do our division. X plus 3 is dividing into x squared plus 0x minus 10. We multiply x by x to get x squared. That's x squared plus 3x. 0 minus 3 is negative 3x minus 10. We have to do one more round. We multiply x by negative 3 to get negative 3x. Now I get to the remainder of negative 1. So you get y equals x minus 3 minus 1 over x plus 3. But again, remember, when you're taking limits, when you're plugging in huge numbers for x, the x minus 3 will amount to something, but minus 1 over a huge number is practically 0. So we leave that off and we just say y equals x minus 3. That's the slant asymptote. And again, we could graph that and say, we're going to graph tomorrow, but we could say the line y equals x minus 3, here's the slant asymptote. This graph might, I'm totally making up what this graph does, but it might do some weird stuff in the middle. It can cross through this, but eventually it evens out back to this thing. Last one. These are different by a degree, but this is bottom heavy. You can only have a slant asymptote if it's top heavy by 1 degree. So no slant asymptote. This is only a horizontal asymptote, y equals 0. All right, we're going to practice this for homework. We're not graphing anything yet. That's for tomorrow. We're just kind of learning and remembering the rules today.